Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to talk about the other fundamental theorem of calculus, and I have it labeled as the FTC number 2. Depending on who you're talking to, what book you're looking at, what website you're looking at, sometimes they'll call this the fundamental theorem of calculus part 1, and they'll say part 2 is the one we've already talked about in our previous unit. Whether it's called 1 or 2 is not important as long as you understand the ins and outs of it. Before we get to what it actually is, we're going to go through a couple of exercises here. You're given two functions below. Both are called f of t. And you're going to be asked to find these two things. You're going to be asked to find capital F of x and capital F prime of x in terms of x. And it gives you what capital F of x should be. It's an integral expression. So pause the video, see if you can use this integral expression here to figure out what capital F of x is. And then if you know what capital F of x is, you should be able to take the derivative of that to figure out what capital F prime of x is. And then we'll talk through it. Okay, so for the first one, we're going to have capital F of x is equal to the integral from 1 to x of f of t dt. So I'm going to have 4t minus t squared, dt. And we should be able to do this, no calculator. So I'm going to have to take the antiderivative here, which means I'll just have the straight bar. Antiderivative of 4t is 2t squared minus 1/3 t cubed. So if I evaluate that, I'm going to get 2x squared minus 1/3 x cubed minus this entire thing, 2 times 1 squared, which is just 2, minus 1/3. So I get 2x squared minus 1/3 x cubed minus, inside of these brackets, I'm going to have 5/3, which is going to give me, I'm going to write this in standard form, negative 1/3 x cubed plus 2x squared minus 5/3. So that is what capital F of x should represent. And then if I take the derivative of that function, right, so this is capital F of x, which means if I take the derivative, I am going to get, using the power rule, negative x squared plus 4x, and that would be capital F prime of x. So I'm not going to take video time to go through all of these other examples because I think now you have an idea of what you're doing. Work through number 2, 3, and 4. Note that numbers 3 and 4, your limits of integration are not 1 to x, they are 1 to x squared. So it's going to change how you evaluate the integral a little bit. So once you've done that, I will then come up and put answers up so you can just check, make sure you have them correct before we move on to our next section of the lesson. All right, so number 2, we have capital F of x being equal to sine of x minus sine of 1, which means capital F prime of x, I'm just going to say f prime of x from now on, is equal to just cosine of x. If we hop down here to number 3, I have f of x being equal to 1/4 x to the 8th minus 1/4. Which means f prime of x is equal to 2 x to the 7th. And finally, for I would pay good money to know why that's going on. F of x is equal to 4x cubed minus 4, which means f prime of x is just equal to 12x squared. All right, so hold on to those answers. Again, now once we learn what the other fundamental theorem of calculus is, the amount of work that you just had to do is going to probably be cut by like 90%. So I had you go through it once to figure out what all of these f prime of x's were, where you first went back and found what f of x was, then you took the derivative. You're going to see that the other fundamental theorem of calculus allows you to find f prime of x rather easily. So let's take a look at the top of the next page, and we'll just get into what the second fundamental theorem of calculus is. So there's going to be two ways that I show you how to write this. The first one is an easier way to think about it, and the second one is a way that generalizes it to, more complex examples. So let's start off with the basic form. If f is continuous on the closed interval a to b, and x is on the closed interval a to b, then if capital F of x is equal to the integral, not from 0, from a to x of f of t dt, then capital F prime of x, well, all that's going to be equal to is f of x. And make sure we note that the a in our limit of integration, note that a, note that a is a constant. So this may look a little confusing. It may not make sense as to what this is saying. So I am going to draw a little example for you on another page and kind of break this down. So let's get rid of this. Let's go to a blank page. So what is this saying? Well, if I have a function, call this f of t and t, let's have my interval here, a to b, and let's put the x somewhere in between, right? We said that the x had to be on the interval a to b. Well, we know that f here is continuous on a to b based on the graph. And then I defined this function f of x as being equal to the integral from a to x of f of t dt. So just take a minute. What does this represent, right, in terms of the graph? Well, this just represents the area, right, underneath the curve from a to x. And again, I'm defining this with a function f of x, capital F of x, because that x can change, right? So if x moves a little bit to the right, that area is going to increase. If it moves a little bit to the left, that area is going to decrease. So all we've written here, capital F of x, just represents a function of the area under the curve. Well, here's where the FTC, this FTC comes in, right? If I want to take the derivative of this function, which would essentially mean how the area underneath the curve is changing at a certain x value. So, right, is the area under the curve decreasing? Is it increasing, etc.? Well, that rate of change in area is going to just be equal to the value of the function at that x value. Right? So you could think about if this x value was, we'll just say it's 8. Well, when x is equal to 8, the green area underneath the curve of f is changing at a rate of 8. And I don't know what the units are here, right? Because maybe this is maybe our units here are meters. Whoops. And down here, they are seconds. So in that case, you could say the rate of change is 8 meters per second. And you have to think, right, this green area, if we were talking about a velocity function, well, that area would represent the displacement of the particle, right? If I just set up an integral that represents the area under a velocity function, that's going to represent the displacement of the particle over that interval. So the derivative of the function that represents the area under a velocity function, right? So this capital F of x right here, that just represents the area, which represents the displacement. So if you took a derivative of the function that represents the displacement, you're going to get how is that displacement changing? Well, at x equals 8 here, the displacement is changing at a rate of 8 meters per second at that specific instant. Okay, hopefully that gives you a little bit of an idea of, what an expression like this represents, right? And all that is that capital F of x function represents a function for the area under a curve. Normally, we would have a definite integral where these two limits of integration are both numbers, but maybe I just want to have a function of that area, so I let one of those limits of integration be equal to x rather than a specific number, which means that area can change depending on what x is. Another question that you may have is, well, why am I allowed to use this graph here for both f of x and f of t? Well, this graph is really just the graph of f. It's not just f of t, not just f of x. It just represents the graph of f. So if I want to change my input here to x's instead of t's, that's fine. I would just think of my y values in terms of f of x values rather than f of t values. But t and x, those are just arbitrary placeholders for what the input to the function of f is. Right? I could call it f of a if I wanted to let a represent my inputs. So when you're looking at a graph of f of t, note that that could also be an f of x value. We are just switching what we're calling the inputs and the outputs. Okay, so this is the basic form of this fundamental theorem of calculus. Now, if we go back up here, let me go all the way back up. Sometimes they won't just have an x in your limits of integration. Let me show you what I mean. I'm going to skip writing the initial criteria again. A criteria for the second fundamental theorem of calculus is that that function has to be continuous over the given interval. So if that is true, then sometimes they may give you a capital F of x function, which is represented by the integral, some constant to a function other than x, right? So it may be like x squared, or it may be 3x squared, or maybe it's going to be something like x over 2. So to get around all the different types of functions they could put at that upper limit of integration, we're just going to call all of them g of x. So g of x represents whatever type of function you could have at that upper limit of integration. And then the rest of it's going to be the same, f of t dt. So if I want to find, so if capital F of x equals that, then f prime of x is going to be equal to f of g of t times, f of g of x. What am I doing? F of g of x times g prime of x. So you're using a little bit of a chain rule here. You're swapping that t out for g of x, but then you also have to multiply by the derivative of g of x. And this is actually exactly what we did with our original example. Again, let me show you. You don't have to write anything else down in your paper. We're just going to go with this, but let me show you how this is related to the basic form that I gave you before. Right? If I change this to just x, we are still doing the same thing, right? Because let me just actually select all of this. Let me get all of it. There we go. Let me just move that down here. So before, we said if we were given this, then f prime, talking about capital F of x, was just equal to f of x. Well, we were still doing the chain rule here, essentially, right? We were still replacing the t with x, and then we were still multiplying by the derivative of x, right? Because the derivative of x is just 1. So it turns out that this just becomes f of x when that function at the top of our limit of integration is x. But again, sometimes it won't be x. Sometimes it'll be x squared. Sometimes it'll be, 3x over 2. So when it's something other than x, this is what we need to think about. And again, this covers all the different types of functions you could have, whereas this example up here just works when that upper limit of integration is x. Okay, I know that was long, but hopefully, that gave you a decent understanding of what the second fundamental theorem of calculus is, and the notation surrounding it. This will also make, the problems we did up above at the very beginning of this lesson a whole lot easier. So let's go through and see why that's true. We'll do the first one and we'll do the third one. I don't think we need to do all of them. So for the first one, if we think about our answer from up above, and page 584 was just the page that I took these problems from in a different book, but those are just our answers that we have on the first page of our notes. We had f prime of x was equal to negative x squared plus 4x. But it took us a decent amount of work to figure that out, right? We had to actually go through and evaluate the integral, then we had to take the derivative of our answer. If we apply the second fundamental theorem of calculus, well, we're going to take this x, we're going to replace the t's with it. So f prime of x is equal to 4x minus x squared. And again, you can think about, we then multiply by the derivative of x. So we multiply by 1, but that's not going to change anything, right? So it's going to be left the same. And I could, of course, rewrite this in a different order if I wanted to. Negative x squared plus 4x. So much easier than going through the process of finding the antiderivative, substituting in those limits of integration, and then taking the derivative of our answer. Let's look at one where the upper limit of integration is not just x, but in this case, x squared. So let's see how we would evaluate that. So again, our answer from the previous page, we got f prime of x was equal to 2x to the 7th power. But again, a decent amount of work involved in finding that. Using the second fundamental theorem of calculus, well, we're going to replace every t with x squared and then multiply by the derivative of x squared. So f prime of x is equal to x squared, all of that to the power of 3, times the derivative of x squared, which is 2x. So I get f prime of x is equal to exponent rules x to the 6 times 2x, which gives us 2x to the power of 7. So again, second fundamental theorem of calculus makes these problems a bit easier. Some of these problems, right, they'll make it so difficult that if you try doing this the way we did on the first page, by evaluating the integral, the definite integral, and then taking the derivative, you're not going to be able to do it, right? The antiderivative would be so complicated that you wouldn't be able to figure it out. So you would have to apply the second fundamental theorem of calculus to evaluate, right? Which you don't even need to find an antiderivative for the second fundamental theorem of calculus. You just have to use some substitution and maybe the chain rule. Let's go through one example. Hopefully we can keep this video under 30 minutes, but we'll see. We're going to look at this example right here, questions 1 to 5. As always, I encourage you to pause the video, see if you can figure out any of these without listening to an explanation, and then come back and join us to fill in any of the missing pieces. Okay, so for number 1, it says, find the value of f of 0. Well, I am given a graph of g of t, and it's said that f of x is represented by the integral -4 to 2x of g of t dt. So for f of 0, well, that just means I'm substituting in 0. So I get -4 to 2 times 0, which is 0, of g of t dt. I don't know the function for g of t in algebraic form. I just know the graph. So I'm just going to be finding the area, right, under g of t from -4 to 0. So this area right here. So I would just need to break it up into the different pieces. Oops, I'm going to have this little triangle right here. It's going to be a negative area. So right here, height of that triangle, 1, length of the base is 1. So that's going to be 1/2 times 1 times 1, and our answer is negative because it's beneath the x-axis, so the area of that piece is -1/2. I then have the same triangle, but up above the x-axis, so +1/2. Then I have a quarter circle and a rectangle. Rectangle, that is going to be, or have an area of 2. Quarter circle, 1/4 pi r squared. So 1/4 times pi. The radius here is 2, so times 4, because 2 squared would be 4. So this simplifies. -1/2, +1/2, they simplify. So I get 2 plus pi. So the answer to that definite integral would be 2 plus pi. Then I'm being asked to find the value of f of 2. Well, same idea, just a different definite integral. So f of 2 is equal to the integral from -4 to +4, 2 times 2, of g of t dt. Well, I'm not going to do all this work twice, right? I already know the value of the integral from -4 to 0. So I get 2 plus pi. And this function is actually an even function, right? It has symmetry about the y-axis. So do you need to do all the work here? No, you don't. You can if you want, but you would see that all of this area, what color should I use? Purple. All of this area right here, that is also going to be equal to 2 plus pi. So here I get 4 plus 2 pi. And again, you could go ahead and break the right side of that down into the same shapes and find the areas of those, or you could recognize that it's an even function, so the area on the left-hand side of the y-axis is going to be the same as the area on the right-hand side of the y-axis. All right, let's move on to number 3. So now we are taking the derivative here. We're trying to find f prime of 1. So the first thing I'm going to do is just find f prime of x using the second fundamental theorem of calculus. So f prime of x is going to be g of 2x, replacing my t's with 2x, times the derivative of 2x. So times 2. So if I now want to find f prime of 1, that's going to be equal to g of 2 times 2. Remember, this graph up here is just the graph of g, whether my inputs are t's or whether my inputs are x's. So g of 2 is equal to 1. 1 times 2 is equal to 2. Let's look at f prime of negative 2. So I don't need to go through all the work to find f prime, right? I can just skip to f prime of negative 2. That's going to be equal to g of negative 4 times 2. G of negative 4 is negative 1 times 2. So we get an answer of negative 2. All right, number 5. Now it says find the value of f double prime of 2. Well, let's clear this a little bit. Let me rewrite. I'll do the work in this space right here. So I know that f prime of x was equal to g of 2x times 2. Now I'm being asked to find f double prime of 2. So I'm going to rewrite f prime first, just to put the constant in front. Then I get f double prime of x is equal to 2 times g prime of 2x times 2. Again, just using the chain rule there. So I get 4 times g prime of 2x. Make sure we know that's g prime. Well, to evaluate, I get f double prime of 2 is equal to 4 times g prime of 4. Well, I don't know what g prime of 4 is because algebraically, right? Because I don't have a function of g written algebraically, but I do have the function of g in graph form. So I need to look for the slope of the tangent line at x equals 4. So right here, the problem is, right, that function is not continuous at x equals 4. It's continuous up to x equals 4, but the function, right, stops at x equals 4. So the limit of the left-hand side does not approach the same thing as the limit of the right-hand side. So the function is not continuous there, which means the derivative does not exist there. And if g prime of 4 does not exist, then I cannot evaluate f double prime of 2. So does not exist because g prime of 4 does not exist. Okay, we will get some more practice in class implementing this other fundamental theorem of calculus, both algebraically as well with some problems with graphs like we just did. But we will cut the video off here. So as always, enjoy the rest of your day, and we will look forward to seeing you for our next lesson.